Hello, my name is Tsai-Hsing Ho. I'm going to share part of my PhD research work with Professor Peichun Amy Tsai in Department of Mechanical Engineering, University of Alberta. This project is motivated by carbon capture and storage in geological formations, in short, CCS. It is one of the promising solutions to mitigate the atmospheric level of carbon dioxide. A CCS engineering is to transport carbon dioxide emitted from industrial facility and inject it into sites such as depleted oil gas reservoirs, deep sea floor or subsea bed, and deep saline aquifers. The injected CO2 is expected to be confined between the cap rock and the base rock, and eventually trapped underground for a long time. To effectively sequester CO2 in storage site, it is important to estimate the storage capacity of target formations and evaluate the sealing integrity of cap rock. For safe injection operations, minimum CO2 leakage, and the least environmental impact. Therefore, the mass transfer behavior of CO2 bubbles in the pore scale become crucial for these evaluations, such as CO2 dissolution rate in water under various reservoir conditions and CO2 phase states. The major challenge to acquire essential data for CCS evaluation is that our study object is deep underground. Take the Quest CCS project in central Alberta, for example. The host formation is about 2.2 kilometers below the surface. Microfluidics can overcome this difficulty because it provides patterns in the micro and nanometer land scale to simulate the tiny pore space in the storage formation. It also offers excellent optical accessibility for direct visualization. Thus, we designed and utilized a high-pressure microfluidic platform to enable microfluidics to function properly in ranges covering the gas, liquid, and supercritical states of CO2, representing the increasing injection depth into reservoirs. We follow a bubble and water pair to record the bubble size change with position and time and extract the volumetric mass transfer coefficient, KLA. This parameter measures the CO2 mass transfer efficiency from the bubble into the adjacent water. Our data show that supercritical CO2 has a more intensive mass transfer than the gas and liquid state. The linear correlation of KLA and Reynolds number Re implies that the increase in a bubble moving speed enhances its mass transfer to water. Finally, this work demonstrates the potential of microfluidics for helping assess the relevant timescale and volume of injected CO2 dissolution in water direct from the lab for large-scale CCS operations. This presentation is based on the manuscript accepted by Lab on a Chip. Thank you.